So one additional skill that you need to have when working with redox reactions is being able to balance redox reactions. Now, we're going to just do the very basic, and what happens in redox reactions that you don't see in other reactions is not only do you have to balance atoms, but you also have to balance electrons. And so when you're writing the half reaction, electrons are going to be placed on the reactant side if you're dealing with a reduction reaction, because in reduction, remember, you gain electrons. And so if an atom is oxidized, then you're going to put the electrons on the product side. So let's look at an example really quickly. So, all right, this tells me to put the correct number of electrons in the correct place. Well, iron has a +3 charge when it's a reactant and then a +2 charge when it's a product, which tells me that this is being reduced because it is gaining 1 electron. So I'm going to put the electron on the reactant side, and it's just 1 electron. So not too bad. Well, here comes the issue. Well, what if each atom doesn't necessarily gain and lose the same amount? When we're balancing redox reactions, we have to make sure that the number of electrons that are gained equals the number of electrons that are lost, and this is how we do it. If you look at this redox reaction right here, zinc reacts with copper 1 ion to produce zinc ion and copper. So what is being reduced? Well, remember, reduction is gain. So which one is gaining electrons, meaning its charge is becoming more negative? Well, copper, because copper goes from a +1 to 0 charge. So copper is being reduced. Well, if it's being reduced, that means it's gaining electrons. And how many electrons is it gaining? Well, only 1 electron, because it goes from a +1 charge to no charge. Zinc is being oxidized, and which means that it is losing 2 electrons because it's going from no charge to a +2 charge. So I'm going to put 2 electrons on the product side. Here's your issue. I need to make sure that the number of electrons I gain equals the number of electrons I lose. So what I'm going to have to do is I'm going to have to take my reduction half reaction, and I'm going to have to multiply that entire thing by 2 in order to make sure that I'm gaining 2 electrons, because I'm going to be losing 2 electrons. So this would become 2 copper ions plus 2 electrons produces 2 copper atoms. And now and only now can I add these reactions together. Notice my electrons cancel out, and what I'm left with is 2 copper ions plus zinc, which produces your zinc ions and 2 copper. So there is a balanced redox reaction, making sure that your electrons are balanced. However many you gain equals however many you lose. So now that you know that there are half reactions, so you've got a reduction reaction and an oxidation reaction, we are now going to put numbers to that. And the term that we use for actually quantifying what's happening in those overall reactions is cell potential. Now, cell potential is how much voltage exists between the 2 half cells. Okay? So we will be able, and I'll explain to you in just 1 second, we'll be able to find the cell potential for a reduction reaction and for an oxidation reaction. And if we actually add those 2 values together, we can find the overall cell potential for the overall reaction that we add together once you have your oxidation and reduction reactions added together. Now, why does that matter? Why do we calculate it? So the cell potential for a redox reaction will let you know whether or not a reaction will occur spontaneously, meaning if you think about, for example, if you think about a waterfall, common sense tells you that water is going to fall from the top and land on the bottom. So when your cell potential is positive, what that means is that overall reaction is going to occur without any outside help. And that means that it is spontaneous. Okay? If, however, your cell potential, which I will show you how to calculate in 1 second, is negative, that is the equivalent of water going from the bottom of a waterfall to the top of a waterfall. And therefore, it's not going to be spontaneous. If water were to do that, there would have to be some sort of outside force pushing the water up, because it doesn't happen naturally. So when we're talking about cell potential for a reduction and an oxidation reaction, when we combine those cell potentials together, that lets us know whether or not a reaction will occur without the need for any help, or if we're going to have to provide some sort of energy, some sort of voltage in order to get that reaction going. And so really quickly as a review, the half cell potential is always going to be listed as the reduction potential.
And remember, if you want to determine the cell potential for something that's being oxidized, you simply take the negative of the reduction potential. And the last piece of information is if a reaction is multiplied by a coefficient, you do not multiply the cell potential. This isn't really an issue yet because we haven't worked with some concepts where you do multiply or raise values based on coefficients. But for these, you ignore the fact that you are multiplying them by a coefficient. So let's look at an example. So to determine the cell potential for an overall reaction, which includes oxidation and reduction, all you do is you take the cell potential for oxidation and add it to the cell potential for reduction. So let's determine the electromotive force for this reaction that's given to you. And so my first task is to determine what's being oxidized. Well, since sodium's going from an atom to an ion, a positively charged ion, that means it lost electrons. So I have sodium, and it's going to produce sodium ions. And I've got to make sure I add that electron there because it's losing one electron. Now, fluorine's being reduced. Fluorine is going to become fluoride. And I got to keep in mind that I'm adding 2 electrons to create that fluoride ion. And so my next task when I'm balancing this is to make sure that my electrons are balanced like what we did previously. So I've got to take the sodium and I've got to take that entire oxidation reaction and multiply it by 2. So have 2 electrons there, 2 sodiums there, and 2 sodium ions there. Now I'm going to look up the cell potential for sodium and for fluoride. Well, the cell potential for sodium is actually the reduction potential. So I find the reduction potential.
And this reduction potential and all the reduction potentials that you'll need to use, just as a side note, will be given to you on the test. Or it'll be in your textbook if you're doing practice problems.
And I'm simply going to flip the sign. So it was negative 2.71 for reduction. Well, since this is oxidation, I'm going to take the negative of that. So it's positive 2.71 volts. Then I'm going to look it up for fluoride, and it is positive 2.87 volts. And so all I have to do to find the standard electromotive force is add those together. So I get positive 5.58 volts. Now keep in mind, I multiplied all of the sodium reaction by 2, but I didn't change the cell potential for that. I didn't multiply it by 2 or anything. So make sure that you're not multiplying by coefficients. And that's all there is to it. Making sure for oxidation that you flip the charge. So if it's positive, make it negative. If it's negative, make it positive. And otherwise, just sum them together.